Okay, so let's start. So a question was just asked, and I think it was also asked on Piazza, but just want to clarify. So on your circuit for design homework number 2, if any of the inputs are invalid, namely if either temp or the set point are invalid, then the too hot LED should be off, and the display temperature display should say minus minus, the middle segments being on. So that means if temp is 000 or set point is 000 or both of them are 000, then your input is considered invalid. 000 is the only missing combination because the other 7 encodings map to valid temperature. So 000 is the only invalid one, and that should result in that sort of behavior. The other comment I had was during office hours, several students came, and so there were several questions. So one question was how much for correctness versus how much for the quality of the design, the cost of the design. We haven't precisely decided it, but I expect it to be like after excluding the points for whether you submitted other things that we asked for, like the test cases and all, we'll basically probably give you 2/3 or so for the correctness and 1/3 or so for the cost. Another question asked was, what cost are we aiming at? So as I explained in a couple of Piazza postings yesterday, Logisim has built-in capabilities for doing circuit analysis. That is, given equations or given truth table, it can generate NAND-based logic or NOR-based logic. So that's a trivial thing to get right. I mean, if you feed the correct equations, you're going to get a design with some cost. So I certainly expect that we should do at least that much and better. Now, last year I had given a problem, which was a variant of that, and I recall there were 3-4 students who got design costs which were roughly 2 to 2.5x better than what Logisim had produced. And the reason is that Logisim only does sum of product or product of sums, and oftentimes by factoring things out more and having more than 2 stages in your logic, you could do better. Unfortunately, there is no single recipe, and of course, there is no particular known answer short of checking things exhaustively. But there would be a relative grading element out there, that is those who have correct design. So if design is not correct, then you're not going to get anything for quality either. But if your design is correct, then quality relative to your peers is going to come into play. Finally, as you think about designing these things, so this system really has 6 bits of input, 3 bits of temp, 3 bits of set point, and it has a total of 15 outputs. There is one output which controls the 2 hot LED, and then there are 7 outputs for each one of the 2 displays. So 7 plus 7 plus 1. So really what we are doing is we are implementing 15 functions. Now, of course, some of these functions may share some logic, which is the way you can kind of gain some advantage over what Logisim would otherwise produce. So when good way of thinking about when you're designing these things is think from output backward. Think about like what's the equation of the output, and not one way I like to think about it, under what conditions is the output 1. In our first homework, there was a problem which basically was something along the lines that there are some inputs, condition A means this, condition B means this, condition C means this, and then the output was in terms of those conditions. Think the same way out here, that what are the conditions that activate a particular output. So for example, let's take too hot. For too hot to be lit, of course, the temperature has to be greater than equal to the set point, but the additional clause is both temperature and set points have to be valid. That is, they cannot be 0, 0, 0. So you have to kind of basically translate this into saying that what are the different conditions and create an expression. Or let's take another example. Let's say we look at the left digit in the top segment. So left digit of the top segment is displaying the tenths digit of the temperature, which in our case are 6, 7, or 8. So it's always lit up, except when either the set point or the temperature are invalid. So the condition in this case will become top left segment is lit up, except when either one of the two are all zeros, either or both of them. So you can kind of express your logic in these terms, and then you'll get your initial equation, and then you can use Logisim to kind of design it. Or I also sent around on Piazza link to Wolfram Alpha, which I like to use quite a bit because it can do a lot more manipulation of Boolean equations. It asks you to write them slightly differently, but it gives you in one go many different ways of kind of expressing that equation. So I find that useful also. And then you can translate them back into logic. The question.
Right, so I know you said that if either of the inputs were invalid, that the LED output should just be like minus. But what was the too hot? What should too hot be?
Too hot is off, right? That's the logic there. If you read that sentence again, I think that's what it says. So that if for too hot should not be lit up if any of the inputs are invalid. But speaking from memory, so just make sure the language. But there is a statement to that effect. So those are kind of some of the feedback comments I just wanted to convey. Any other question before I dive into the lecture? Okay, so the other thing is on Monday, the lecture, I would like to spend time going over the review. For review to be successful, so I don't want to repeat the lecture, it's kind of pointless. So for the review to be successful, I need you guys to send me problems, okay, so that I can go over them. There's a question about how best to prepare for the midterm. Do as many of the problems from the back of the book as you can. That's kind of your best strategy. The midterm would have some kind of problems which would be simple, and there are probably one or two problems which will go beyond it's not just a straightforward application that do a Carnot map or something. It will be couched in some sort of a design type language, and you'll have to kind of apply your knowledge out there. So there'll be some twist to perhaps a problem like that. But the best thing you can do is to do as many problems from back of the book. It has a very rich collection. Now, if you're running short of time, you would see that the way this particular book is structured is the problems at the back. Sometimes they pick up a theme like 7-segment display, and then they have a whole bunch of problems on them. Okay, you don't have to do all of them. You can pick and choose, and that will give you a good enough exposure. But try to do as many different types of problems that you see in the back. The other thing, needless to say, you have had more exposure to the material we covered earlier in the class. So hopefully you're well versed in that. It's a newer material which we've been covering in the recent couple of lectures and today, where you need more attention. So I would say try to solve problems from the book relating to those. They basically boil down to how do you design things using building blocks. So you should be comfortable with that. Various kind of building blocks, how could I create stuff around that? We'll see some more examples of them today, but that's where I would say put some attention to, because you have had less time to assimilate them. Okay, any other question? Good. So let's start. So the very end of the last lecture, we had started, we had done this priority encoder, so I just want to go over again. So we had seen arbiter before that, and arbiter, if you recall, basically took n inputs and then basically decided who is the winner. And the definition for us was we always started from bit number 0. So we said bit number 0, if it wants the resource, it will get it. If it does not, then we check bit number 1, and so on and so forth. So bit 0 had the highest priority, bit 1 had the next highest priority, and so on and so forth. So that was our arbiter. Priority encoder builds upon the arbiter. So what priority encoder does is, it basically takes a n-bit number, and it basically, again, starts from bit location 0, and which says, what is the smallest bit position where I see a 1? And I want to output the bit position. So if I have n bits, then I need to encode the bit position. So I will need log to n ceiling that many bits. In this case, So in this particular example, which I had done kind of last time around, I have 8 bits, and the pattern was 0, 0, 1, 1, 0, 1, 0, 0. We start from the right in this example, and we see that in bit position number 2, we encounter the first 1. So we want to output 2, as in 0, 1, 0. So that's what we want. We want to output which bit position is the first one to have a 1. So the way to kind of do this thing is that we basically make use of the arbiter and the encoder. So the arbiter would take this, and then it would output a 1. It would have as many bits as output, so it will output 8 bits, but it will output a 1 on only one of them. And the one it will output a 1 on would be the one corresponding to the earliest bit, which has a 1, because we gave 0 the highest priority in our arbiter. So what will happen is, if we look at this G, then in this particular example, G will look like 0, 0, 0, 0, 0, 1, 0, 0. So basically G of 2, second bit position of G, as in 0, 1, 2, that would be high, the rest would be 0. So that's just a straight arbiter functionality. So arbiter is basically doing a one-hot coding of the bit position. And then we use an encoder and feed this thing, and output will be 0, 1, 0. So by ganging or cascading an arbiter followed by an encoder, we basically get our priority encoder. So this is an example of how, when faced with a new function, if I let you, that is, if I don't explicitly say that, hey, you have to use an AND gate or things like that, then you should do things in terms of these modules. And in Logisim, again, you have a whole bunch of modules available in the library, and you could kind of make use of those. Now, there's a slight disconnect between the modules that the book provides and the modules that Logisim has. So when you are doing homeworks and all, I expect you to use the modules that are in the book and in our lectures. But when you are doing a Logisim design later on, not this particular design assignment, then you will have to use the modules that it provides, and they are slightly different in behavior, and I would like you to just read the user's guide to kind of see what it is. But it has counterparts to a lot of these stuff that we are talking about: encoders, decoders, multiplexers, and all. So let's look at building some more complex blocks, and in particular using decoders. So we want to create an equality comparator. So what this equality comparator does is, it takes two n-bit inputs, A and B. We think of those inputs as representing binary numbers, let's say, and we want to output if the two numbers are equal, or some bit pattern, and we want to output if the two match bit to bit. So like, for example, if n equal to 4, then A may, let's say, receive 0, 1, 1, 0, and if B also receives 0, 1, 1, 0, then the output should be 1. If B receives anything else, then output should not be 1. So we want an exact match of the binary string. Now, if you go back to one of the very early lectures when we had talked about XOR gates, we had XOR and XNOR. XOR had meant that a 2-input XOR gate, the way it worked was that the 2 bits, if they are one and only one of them is 1, that is, not both are 1, so exclusively, one of them is 1, the other 0, then the output was 1. So XOR outputs 1 if the two inputs are 0, 1 or 1, 0. XNOR does exactly the opposite. It will output 1 when the 2 bits are either 0, 0 or 1, 1, the 2 inputs. So XNOR is an equality checker for a single bit. In this case, what we want to see is that all the bits, corresponding bits, are the same. So what we'll do is, we check A0 is equal to B0. We'll also check A1 is equal to B1, A2 equal to B2, A3 equal to B3, and that we do by the XOR gate. And then we want to make sure that all of them are equal. So therefore, we have an AND gate, and that's what we kind of feed them in. So this gives us our 4-bit equality checker. Of course, this principle is extensible to more bits if you need. But that's kind of the basic idea out here. So this is simple. Now, let's say we want to, equality is good, straightforward, but let's say we want to do something more complicated. We want to do a magnitude comparator. So, in case of magnitude comparators, we are going to look at these two inputs, A and B, and we are going to think of them as binary numbers, positive binary numbers. So they'll have a value, a decimal value corresponding to each one of them. And what we want to do is, we want to design this circuit so that the output, which we call as GT, it is high when, if and only if A is greater than B. So let's say let's say N was 4, let's say A was 1000, which is the number 8, and let's say B was the number 0110, which is the number 6, then A is greater than B, so output would be 1. If on the other hand, let's say both were the same, 100 and 100, then A is not greater than B, and the output would have to be 0, and so forth. So how should we do it? So before we dive into the design, think about how do we compare numbers. So let's say I ask you to compare two 3-digit numbers. So forget binary. Let's say just look at regular decimal. So let's say I give you two numbers, 172 and 243. So 172, 243. How do you go around comparing these two numbers? Compare so compare the hundreds place. In this case, 100 place were 1 and 2. 2 was greater than 1. We are done. So 243 or whatever I said is greater than 172. Let's say my numbers were 172 and 178. 172 and let's say 188. So now hundreds digits is the same. So now we need to skip to the next one. I'll check 7 and 8 and pick the one corresponding to 8 and stop. Or in the worst case, my situation may be something like 172 and 175. So hundreds is the same, tens is the same. So I have to then check things at the unit position level. So that's how we compare numbers. It's the same thing in binary, except that instead of hundreds and tens and ones, we have to worry about 8s and 4s and 2s and 1s, right? So we just have to worry about powers of 2. Same concept out here. So let's see how it kind of plays out. So let's say we have these two numbers, which are 6 bits each. I have A, which is 001110, and B, which is 001011. Firstly, which number is greater? A, right? Because the prefix 001 is the same, and then in position number 2, A has a 1, B has a 0, so that's wins out. So we want to somehow emulate our intuition, same approach, that we are going to start with bit 5, see if there is a winner. If bit 5 leads the winner, we stop. If not, we go to bit 4 and so on and so forth. So we are going to mimic that process. And the way we are going to do it, we are going to create a comparator for each bit position. A bit like the way we had done for the arbiter, where for each bit position we were getting an input from the previous bit position, we are going to do the same thing out here. The only difference is here we have to start from the left side, the more significant bits, right? They are the one which first tell us. So we'll have some logic sitting in each bit position, and the higher bits are going to tell the lower bits whether there is a winner thus far. So we are going to, so our logic looks like the following: that in any bit position, we are going to take the corresponding bits AI and BI, and we are basically going to say that so the condition under which we have a greater happening is the following: that A is greater than B if the number A is greater than B if AI is 1 and BI is 0, and we did not have a winner previously. So the higher bits were all equal. So that's kind of the interpretation we would like to do. So GT equal to 1 if and only, let's look at this logic. So this logic, what's happening is, the first one is saying this AND gate with a bubble is basically checking, it's going to be high if A is 1, AI is 1, and BI is 0. So it's basically saying at this bit position, A is greater than B. If I were to just look at this bit position, so we assert we say a GT of I out there, but that's not enough for us because we also need to see whether what has happened in the previous stage. So we are going to say that there is a GTBI coming from the ith from a previous stage, and there is a GTBI plus 1 which is going to the next stage. So GTBI equal to 1 indicates that okay, so I guess in this one we are working the reverse way. So let me stop for a moment. What GTBI in this logic is going to indicate is that for 0 through I minus 1, input A is greater than B. So if I look to the right of this position, whatever is the number, it has decided it is greater than that. It has decided that A is greater than B. Okay, so if this is 1, A is greater than B, and now what we are going to send out is the following: that if until for the lower bits A was greater than B, and for this bit A was equal to B, that means for the next stage I'm going to say still that for the lower positions for now for 0 through I, A is greater than B. If on the other hand in this bit position AI is greater than BI, then nothing else matters because that means that now the number A is greater, so we don't even need to care about that. So this is working slightly differently from the logic we were using otherwise. So what is happening is we are going to start out here. So at bit position 0, we will say B is greater than A because B is 1, A is 0. And therefore, we will tell the next stage A greater than B is not true. Then we come out here. Here we see AI in position 1, AI and BI are both high. But previous stage told me that B is greater than A. So after bit position 1, we still have that B is greater than A, or another way of saying A is not greater than B. Then we hit bit position 2. In bit position 2, we see that A is greater, A is 1, B is 0, and therefore this supersedes and nothing else matters before that, because in this position A supersedes. So the next stage we are going to tell that A is now greater than B, and we kind of keep doing that, and eventually out of the left we are going to get the logic whether A is greater than B or not. So we are doing kind of the same thing that we are starting out, but we are doing from the right hand side now. Or another way of saying is if I pick my numbers 172 and 241, let's say, so now we are starting from the right. We check the, so 172, 241. Units place, 172 is the winner. We come, so we tell that, we come to the tens place, 172 and 241, well, still 172 is the winner. So we go to the next stage, and now we see that 2 is the winner, so we say 2 is the winner. So we can apply the kind of the same logic from the other direction, and that's what the circuit out is still doing. Instead of coming from the MSB, it is coming from the LSB. So at any point in time, we know whether the number to our right, the bits to the right, who is the winner, and then we look at our current bit. If the current bits are equal, we retain the same winner. If the current bit indicates a different winner, then we swap the logic. So, so in this case, GTBI is going to say that bits number 0 through I minus 1 indicate that A is the winner. And what this is doing is it is saying that if A is equal to B for this bit, we will just pass this thing through. If on the other hand A is greater than B out here, then we are going to force it to be 1 out here. If A is smaller than B, then what will happen? If AI is 0 and BI is 1, then I will be 0 and GT sub I will be 0. So we'll have 0 here, we'll have 0 here, so the output would be 0, which makes sense also because again A is not greater than B. So that's the logic for a single stage. We are looking at winners from the lower bits, and then deciding what to pass to the next stage. You could also design the logic the other way. You can start from the top and kind of do the earlier example that sort of I was presenting. And then our comparator just becomes ganged up like this. I put a copy of this stuff, this logic, and each of the bits, and then from originally out here, we are going to feed in a 0 because A greater than B is not true because we have not encountered any bits, and output that will come out at the top would basically be high if A is greater than B. So let's work out an example to make sure that we kind of are comfortable with it. So let's pick a number. Let's say our number is, let's say, okay, so let's, okay, so let's look at this. So we are starting out with lowest stage is saying 0. On this stage, A0 is 0 and B0 is 1. So what will happen is the X sub, the signal out here, it's not equal. So this is going to be 0. And A is not greater than B, so this is going to be 0. So we are going to get 0, 0, everything will be 0, and we're going to get a 0 out here. So what this 0 is representing is that thus far, starting from the least significant bit, A is not greater than B. Then we come to this stage. Now, in this case, A1 and B1 are both 1 and 1. So this XNOR, which is checking for equality, will have an output of 1. So this would say 1. This AND gate, it is checking whether AI is greater than BI. It is not. So GTI is 0. And now what we'll have is 1 here, 0 here, AND of 1 and 0 is 0, 0 or 0, we again get a 0. So this is basically saying the lower two bits, A is not greater than B, and that is true because A was 1, 0, whereas B is 1, 1. Let's try the next stage. So I'm receiving a 0 here. What will I get out here on the output of XNOR? 0 because they are not equal. And what will I get for 0? And therefore everything is 0, we get a 0 out here. Finally, what will I get here? X0, 1, and 1 all 0, I'm going to get a 1 out there, right? So in this case, by the time we reached end, we kind of got the right result. And so you have to ponder over this logic, but sort of it's kind of the opposite of my decimal example where we were starting from the top. You could design a comparator that way also. You can design a comparator which starts by looking at the top bit and then kind of walks downwards. Now, in the homework, in the design problem, you have to compare the set point and the 10. And you could do it this way, or because there the number is so tiny, there's 3 bits each, you can just directly kind of do it as a sum of product of sums.
The XOR bit, what is it without the little knot in the front?
XOR bit, what is it without the knot in the front?
Is it just
You tell me, someone, what is it? What does an XOR do? If XNOR checks for equality, what will if XNOR checks for equality, what will XOR check for? Non-equality, right? So that's one way of looking at it. The other way of looking at it is saying that one and only one input is 1. Okay. Now for the 2 input case, that is indeed the thing. Now when it comes to, let's say, 3 input XOR gate, then the definition is actually a little bit tricky. Some people say that, generally speaking, if I have an n input XOR gate, Some people say that the n input XOR gate means an odd number of inputs are 1. Okay. Some people say that an n input XOR gate means only one input is 1. And there are both camps. If you read the Wikipedia article that describes this issue, IEEE, which is the electronics organization, I guess they set some standard and all, which basically kind of picked one definition, which I believe is the one which says an odd number or 1. Okay, but it's ambiguous for more than 2 inputs. For the 2 input case, so again, one way of saying is checking for lack of equality. Another way of saying is checking for only one input is 1. Or third way of saying is checking that an odd number of inputs are 1. Okay, that's all the same.
So is that thing over there, is it considered a NOR right now?
Is it considered what?
If it's a not in front of an XOR, is that considered a NOR?
Is it considered NOR? No.
Like the gate. Or what is that considered?
You're referring to just this part?
Yeah, with the not in front.
Yeah, it's called XNOR.
XOR?
Yeah, XNOR. And this little gate and on top of it and with a bubble, it has no name. I mean, it's an AND gate with an inverter at one of the input. There's no standard name for it. Okay, so we have our comparator. Relative to a comparator that you might design as a sum of product, I mean, I could always take my 4-bit number, 2 4-bit numbers. I have now 8 bits of input. I can create a truth table which has 2 to the power 8 entries, namely 128 entries. I can find which minterms are true and do a sum of product implementation, or I can do a product of sum implementation. In that case, I will have only 2 stages of logic. I'll have an AND stage and an OR stage, or I could map them to De Morgan's to a NAND followed by a NAND. In this case, I have to go through 4 stages of logic. So it's the usual trade-off that we have seen previously also, which is I can have potentially fewer gates at the cost of a higher delay. In this case, my delay kind of goes all the way like this, right? So that's the, it's called the critical path. What that means is in the worst case, my signal will have to start at one of these inputs, which are at the bit position 0, and go through all that logic to generate the signal. Given the data pattern, I may have a shorter delay, but in the worst case, I may see something like that. So that's the disadvantage of these kind of logic where we are cascading stuff across bits. Our arbiter was like this is like that. It usually results in a more compact design, but usually results in a slower design. And that's kind of the trade-off that one often has to make. This kind of design approach, where I design one bit and then stack them up, has an engineering advantage, which is if I now tell you, give me a 5-bit comparator, all you have to do is put one more stage out there. Whereas if you had the truth table-based approach, you'll have to start from scratch. You'll have to create an entirely new design. So this kind of approach is often called as bit slice. So this is a term it's called. So it's basically I'm taking my design, slicing it into 1 bit. I design 1 bit and I just replicate it. So it just simplifies the design process considerably. You design once, you optimize it very carefully, that 1 bit, and then you just gang it together. Whereas if you don't do a bit slice type design, then your workload goes up, although it's quite possibly you may result in a better design that way. Question? What is the critical path? What's the critical path length? Or what's the question?
What is
The critical path is referring to the longest path, that longest delay that may exist. It's possible that this bit may change from 1 to 0, let's say, and the effect of that will percolate through these gates, and finally kind of reach all the way up there. So it's the path through which bit changes propagate through. What's the longest such path? That's why it's called critical. Okay. So in this case, in the worst case, for some input pattern, it may happen that a change here goes through this XNOR gate, goes through these stages, and then finally affects GT. So we can see, like in this particular case, unfortunately, that will not happen. But let's say all my upper bits were the same, let's say, and the lower bits, a low change in the LSB can affect things now. So let's imagine A and B were both, let's say, 0, 0, 0, 0, 0. Okay, so the output would have been initially 0. Then let's say B changed from all zeros to 0, 0, 0, 1. So now LSB changed, and as a result, A changed to 0, 0, 0, 1. Then you would see the effect percolating. So let's see how it will play out. So let's forget this old example. Let's consider this. Starting out, everything was 0. So what would be the output? Output would be 0. Now let's say A0 changed to 1. What would I expect the output to be? 1 now, right? A is greater than B. So this will change to 1. Nothing else changed at the inputs. So that means the effect out here had to flow through all this logic and then affect this guy out here. And therefore it is going through this long path, and that's the critical path. And we'll see the same kind of thing in our arbiter design, long critical path. So these bit slice designs often exhibit these kind of paths which go through all the bits. They add to the delay, but they are a compact design. They're a modular design because I can easily kind of create designs with arbitrary number of bits. Yeah.
So I think the critical path should be from the B not input, B0 input to the output. Right?
That is correct, because the XNOR usually has a longer delay than the AND structure. So the critical path actually would correspond to a change out here affecting things. Okay, but I was kind of glossing over it. I mean, I was basically assuming that these two have the same delays. But you're right.
Even if they say that this one has a one more, and
There is one more gate. Yeah, you're right. My point here is going with this long path which is straddling all the bits. Okay.
how many critical paths?
Huh?
How many critical paths does the design have?
In this case, the design has a single critical path.
Don't have multiple.
It's possible that a design may have multiple critical paths in the sense that they may all have equal delays. You often see that. So we'll look about delays really at the sort of towards the end of the course more. Okay. Another implementation of this magnitude comparator can start from the other direction, the way I had originally motivated comparison. So in this case, what we do is we design a logic which now receives inputs from the higher bits, and the higher bits are basically going to tell it two things. One, whether one is the input called EQAI, and the other is GTAI. So EQAI says that for bits number I plus 1 through n minus 1, A is equal to B. And GTAI says that for bits number I plus 1 through n minus 1, A is greater than B. So I have two inputs coming in. One saying upper bits are equal, the other saying upper bits A is greater. And then what I'm doing out here is I'm going to, let's look at the equals. So I will tell the next lower bit that I through n minus 1 are equal if from the previous bit I received equality and AI plus AI and BI were the same. So that's the logic you are seeing out here. This is basically saying that that bit number I will tell bit number I minus 1 that I through n minus 1 are equal if bit I is equal and the bit I plus 1 told that everything above was equal, right? So the upper bits are equal and I am equal, then I tell the next bit also that everything is equal. And the greater than has the same logic. If upper bits tell me that they are greater, A is greater than B, then I just pass it through. So that's why you're seeing GTAI just passes it through out here. If on the other hand, the upper bits are upper bits say that they were equal, then I look at whether on this bit position A is greater than B or not, and that's the logic out here. This AND gate out here is saying that upper bits were equal, and at this position A is greater than B, and therefore I pass that through. And so I kind of keep passing this stuff through, and eventually at after bit 0, I will look at the signal GTA 0, and that will tell me whether A is greater than B or not. So this was again kind of the original way we were doing, where we started out from the most significant digit and walked down. Previous design was walking up. Both are fine. As you can see, this design has some more gates because it's carrying 2 wires through, so it's costlier, but still it too will have a critical path which is straddles all the n bits. Question?
In the previous form, this form, they all share that if they're the same, they're going to be either 0 or 1, right? Is there a way to check whether they're the same without thinking that it's either A is greater than B or B is greater than A? Because the way this is formed, like, if they're the same, they're going to output 1. That make me think, oh, A is greater than B instead of them being equal. Is there a way to check if they're equal?
No, I don't think I understand your question. Which output are you talking about?
So, like, let's say if A and B are both 0, 0.
AI and BI, you mean?
Yeah,
Okay.
AI and BI.
Hmm?
And for the rest of their numbers, they're A and B, all of it, they're equal. For AI and AI plus 1 and AI plus all the way to n, they're the same.
Mm-hmm.
At the end, the code's going to output 1, correct?
Okay, let me make sure I understand. So let's do the following. So tell me the value of A that you want.
0, 1, 1.
0, 1, 1. And value of B?
0, 1, 1.
Okay. So firstly, is A greater than B? No, we want a 0 out here, obviously, right? Okay. So now let's see how things will fare in this design. Okay. So this is how this design looks like. We are going to start out with, and the most significant bit, equal being 1 and greater being 0. So in our example, in your example, you wanted me to do 0, 1, 1. Okay. So we have 0, 0, 1, 1, 1, 1. And we are going to make the inputs out here to be 1 and 0. Okay. So this is saying, this is at the starting point, we are basically saying everything before me, which was nothing, is equal, and A is not greater than B. Okay. If you work through this logic, I'm again going to get 1 out here because this AND gate would see a 1 coming in from here, and A2 is equal to B2. So it will see a 1 out here, and we'll see a 0 out here. And the same logic will flow through 1 and 0, 1 and 0, and this is our greater than. So output here would be 0, which is what we want.
Output will be what?
Huh? Would be 0, right? Because A is equal to B, but A is not greater than B, right? We want A greater than B, strictly greater than B. Okay? Now, in this particular case, this circuit also gives me the equality. So this is actually both doing a greater than comparison and also an equal to comparison. If I ask you to design greater than and equal to, greater than or equal to, then you just put an OR gate at the output of these two and you're going to get that. So you can create other kind of comparators out of these basic ideas. If I want to say, give me less than, A less than B, then there are 2 ways of approaching it. One is I just swap B and A. I just rewire the circuit differently, or the other is I kind of put some negation logic and output.
Why do you start off with 1?
Why? Okay, so the intuition is 1 is basically saying, are the numbers equal thus far? Since I haven't seen anything, so yeah, they are equal. Okay, and the other one is saying, is A greater than B thus far? I have not seen anything, so therefore I cannot assert that A is greater than B.
Is it just for this design, or is it?
It's just for this design. For every design, you have to think of what the boundary condition is. Okay, that's really going to be specific to the logic. In our previous design, which we had seen here, our boundary condition was 0, right? So it will depend on design to design. Yeah. Like for example, oftentimes we are given adders, and we'll see later on the next slide set, and there's a carry in at bit 0. we usually tie it to 0 because there was nothing coming in. Okay, so the carry in to the units position is 0. So now let's say we have our comparator. Now let's say we want to design a maximum. So maximum function, what it says is, it's the larger of A and B. So if I have a comparator tells me whether A is greater than B or not, and then I can control a multiplexer using that and select A or B. So the idea is that in this case, I feed A and B to the magnitude comparator. The output out here tells me whether A is greater than B or not. If A is greater than B, then the control input to the mux would be high, and it will select the top input, which is labeled 1. So A will flow through, so the output would be A. If on the other hand, A greater than B is 0, then B will flow through, and that is the definition of max. You can similarly create min, you can create other similar things. So think about like other things like, for example, how would you do a median? I give you, let's say, 3 numbers. You want to find a max of that. You want to find a max or min of 3 numbers. You want to find the middle of the 3 numbers. All those kind of problems become solvable using some appropriate combination of these things. So mux and comparator, you can then combine them to do some interesting stuff. So mix, match. And when I was saying that for midterms, I expect you to be able to do these kind of things. That's what I kind of meant, that now that we have these powerful blocks, I would like to think about how you can compose even more difficult things by tying them together. And really, at this stage, it's not about digital design so much as kind of mathematical reasoning. Yeah.
Will we, in like a test situation, will we ever just be able to have like a black box magnitude comparator at our disposal, or like will we have to?
Yeah, I'll tell you as part of the thing. I would say you can use magnitude comparator, or you can use any block that we studied in the class. Okay. In fact, if you look at homework 2, which I kind of shipped around yesterday, right, it already has some problems. So, and that's how you would do things again in real life also. Okay. So only when I explicitly say you are limited to using these, then you stop it. Any other question before we move on? Okay, so final very powerful block, read-only memory. So what is a memory? Anyone, like how do computer memories work? You buy DRAM, what do they do? What do they have? Like what's the functional description of it?
Don't they store a potential on capacitors?
Okay, they store charges on capacitors, and those are the ones and zeros. But from a functional point of view, what do memories do? Store data. But how do you know where is the data stored? Huh? With an address. So a memory is a bunch of mailboxes. Each mailbox has an address. When I'm writing to the memory, I tell the memory, write to this address. When I'm reading from the memory, I tell it, read from this address. Okay, so there's an address. If my memory, when we say, let's say I have a 1 kilobyte memory. I have a memory which is 8-bit wide and has 1K words, then that basically means that its address is going to be sufficient to store 1024 in binary, so it would be 10 bits, and so it would be a 10-bit address, and then in each address I'm storing 8 bits. So there are 2 data points for important. How many addresses? And you need log2n ceiling number of bits per address, and then how many data bits at each address. So that's how memory works. All memories. I mean, the rest of the stuff is about like how do they actually store the ones and zeros. There's a one way, but DRAMs do it is by storing things in capacitors. There are other kind of memories that store things differently. Okay, so that's how memories work. Read-only memory, as you can imagine, you cannot write to them. Okay, so you may say, well, I mean, that's useless if I can never write to them. Well, of course, someone writes to them, they write it at the factory. So you get a memory with the content written in it, or oftentimes more common nowadays is that it's just harder to write to them. You need high voltage, or you have to blow some fuse or something like that. So you cannot just write to them in software willy-nilly. you have to take some special action. So they are often go under the name of things like electrically erasable memory or things like that. EEPROM, EEPROM. And then finally we have our flash memories. Flash memories are also writable, but again it takes a little bit more effort to write to them. So for example, so all of you know flash memory and SD cards and all, right? Unlike our DRAMs and all, where I can selectively write to one place, in Flash, when you write, you have to write to a group of words. So let's say I have data stored in the Flash. I want to modify just one location, one mailbox. I actually have to read or whatever. I have to kind of write to a whole bunch of mailboxes simultaneously. That's how Flash is. So they're harder to write. Okay, so those are memories. So ROM is the special case where we're assuming that the technology is such that we cannot write to it or cannot write to it easily. So now all we can do is read from it. I can give it an address and it can return me an n-bit values. So if I have a ROM which has 1024 locations, it will take a 10-bit address corresponding to 1024. 2 to the power 10 is 1024. And then if the memory is 8-bit wide, then it's returning me an 8-bit number. This implements what you can think of it as a function, right? It is mapping address to the value which is stored at that address, right? Any mathematical function is like that. Any mathematical function, if you go back to your some math class, you'd have learned that a function is a mapping from one set to another set, right? I mean, that's what a function is. So a ROM implements a function. It takes as its input the address, it spits out as an output the content of that address. Another term that sort of people in CS like to use are things like lookup table. I have a table, I tell the lookup table which row am I interested in, and it gives me the value in that row, okay, that mailbox. So plain description then, it's a lookup table which has 2 to the power n entries. So my address is n-bit, and so I have mailbox numbers 0 through 2 to the power n minus 1, and the output that is on each address, I have an n-bit value stored. So I have 2 to the power n locations, and on each location, I have a unique, possibly unique n-bit number stored on there. So I may have n equal to 10, m equal to 100, in which case it's a lookup table which is taking 10 bits input and producing 100 bits of output. I can change the output bit width of a ROM, or I can change the number of address bits in the ROM. But if I have a ROM, then I can implement, as you can imagine, any function. Any function, in this case, any function that goes from n-bit to m-bit. So it's a universal combinational logic, right? I just arrange for the factory or my special ROM programming hardware to write the appropriate contents in the different locations, and I have my combinational logic. Okay, so you don't have to do any of your Karnaugh map designs or anything like that. You just write the content. You're literally writing the truth table entries into this. So that's the power of ROM. It's obviously comes at a cost. It's less efficient than it's less efficient than doing it kind of the gateway through gate logic and all, but it gives you a general mechanism for doing it. So how are ROMs implemented under the hood? A little bit of in that. So what happens in ROMs is that they are usually implemented using a combination of tri-state buffers and decoders. So if I want to design ROM which has B output bit, B bits on the output, so each location is storing a B bit word, and if I have 2 to the power n locations, that is my address is n bit, then I could implement it this as shown out here. What I have is I have a decoder. It takes my address, and then it does a decoder takes a binary coded thing and outputs a one-hot coded stuff. So on the output, I will have 2 to the power n lines. Each line is selecting a mailbox, right? So I started out with n bits, n address bits. I decoded them so that I have a line for each of the possible memory location. And then what I do is each one of those memory location, I think of it as a bunch of tri-state buffers. Okay, and they're controlled by that bit. So what's happening out here, if you look at this very top, what I really have is this logic out here. What I really have is I have a bunch of tri-state buffers. Specifically, I have B of them going from 0, 1 through B minus 1. All of them are controlled by the same signal, which in our case is W0, let's say for the top one. So they're all controlled by the same signal. If W0 is 0, then these tri-state will be floating. If W0 is high, then whatever I connect their input to, which will be either tied to 1 or 0, so like for example, I may have, let's say, 1, 0, 1 out here, then whenever W0 is high, tri-state switches will be on, and I will see 1, 0, 1 out here. If on the other hand W0 is 0, then I will see high Z, high Z, high Z. So that is how one group of buffer will behave. But now what we have done is, we have done this thing for every memory location. And we tie together the outputs of their tri-state buffers. So what you see out here is, this tri-state buffer, which is really a B, it has B bits in it. It is feeding into a B bit bus, and the corresponding pins of each one of these memory location, corresponding output of tri-state buffers at each one of these memory location connect to the bus. So what will happen is, given an address, exactly one of the decoder output will be high, and the corresponding tri-state buffer, its data will get connected to this bus. The others will be cut off because they're off. And then out here, after this is just a plain buffer, it just is used to boost up the signal. I'm going to see my data out there. So address through the decoder selects one and only one of these tri-state buffers, and the content sitting on the input of those tri-state buffers appears on this on these data lines, and then they appear at the output of the memory. So ROM could be implemented using the two modules we saw previously, decoders and tri-state buffers. The magic in ROM is that you want ROMs to be stored a lot of data on silicon. So they are laid out very carefully so that all this design is like compacted and very small, very area efficient. But the basic concept is basically just this. I have decoders, I have tri-state buffers. I'm going to turn on just some of the tri-state buffers, the ones corresponding to my address and nothing else, and then kind of output it. So that's ROM. It's not commonly used nowadays to design logic, but it's used quite a bit when you are writing, like in software and all. Like you may have long tables and all, and you kind of so you're implementing a function. You may just create a lookup table and then store it into a ROM area. So, for example, let's say you are writing code for doing some funky mathematical computation on a very simple processor, which doesn't have a whole lot of horsepower. Like, let's say you want to compute sine, cosine, or exponent, or some other complicated function. Then one way to do it is to come up with an algorithm which sort of computes, let's say, sine. That could be pretty tedious or complicated for a low-end processor. So oftentimes what is done is you create a table. You pre-calculate values of that mathematical function, sine, let's say, and store them into a ROM, into some non-writable, some constant area of your chip. And then whenever you need like sine of 90 degree, you convert that into an address. You look up in the address, you have your value of sine. So ROMs are often used for this kind of purpose. ROMs are also used to store the initial software on your computer. When you hear terms like firmware or bootloader, those are portions of code which are the very first thing your computer system or your appliance runs before it kind of enters into its regular function. And those also usually sit in these kind of ROMs, also somewhere buried deep inside. So they're very commonly used, less so as a combinational device, more so nowadays for storing lookup tables and startup program code. Any questions on this before? Okay, so large ROMs become a little bit trickier. So let's look at this example again. Let's say n was 32. Okay, 32-bit address. So how many lines do I need out here? What is 2 to the power 32? Huh? Yeah, what is it? How big is it? Huh? 4 gig, 4 giga, right? 4 billion. That's huge number of lines, right? So question then becomes, could I do it with fewer lines, right? I mean, having billion wires running across the chip is going to be a huge problem. So what do we do? I mean, so like also oftentimes when instead of like things lined up, we create grids. So one of the things you can do is create a 2D grid. So what I'm going to do is I'm going to divide my 32-bit address into two 16-bit addresses. Okay, one 16-bit address will tell me which row. The other 16-bit address will tell me which column. Okay, so now I only have, what is 2 to the power 16? How big is that? 65,000 or so. Okay, so instead of 4 billion lines, I have 130,000 lines. Okay, big improvement. Okay, so that's what's happening out here. So we basically do this row and address, row and column thing. So I take my address, I divide it into row decoder and a column multiplexer. So what's happening now is I'm going to first select which row, and I'm going, and internally I have a data line for each one of the corresponding to each column. So let's say I ended up selecting, let's say, I don't know, I have a simple figure out here. Let's say I selected this row. So the tri-state buffers in this row will be on, tri-state buffers in all the other rows will be off. So whatever is stored in this row will come onto these data lines, the vertical lines that are running. But I'm interested in only one of those columns. So that is where our multiplexer comes in. I am feeding the other part of my address, other half of my address to this multiplexer, which is going to select one of these lines. So let's say maybe it was this line that I was interested in. So so that would get connected, right? So by using this combination of decoder and multiplexer, I basically am able to select precisely the cell I want, which in this case would be this guy, right? Its content. So it is the right row and the right column, and it comes to the output. So when chips are designed for memory, they are usually, instead of laying out all the memory cells in a line, because then I will have a huge line and a huge decoder, you kind of divide it into two, usually design it as some sort of a rectangle or a square. You have a lot fewer lines to work with. Of course, the delay goes up now because I have added this additional stage. So it's a usual game that we have, usual thing we have seen again and again in the past, which is there's always some sort of a area versus delay trade-off, and that's what we are seeing here also. So that was ROMs. If you have a ROM, then you can implement arbitrary logic functions, but it's not the most efficient way of doing things. When people design these chips, they actually design this little part, each cell. They kind of put a lot of effort to make it very tiny, because when you are buying memory which has several gigabits, then these things add up. So you would normally see that memories are the places where most advanced technologies first come into play, because we are a data-hungry society, and I think just packing as many, ability to store as many bits as you can on the silicon is just extremely kind of important. And in recent years, I'm sure you would have noticed that hard drives have given way to flash memory. So a lot of our computers now have terabytes of flash, so you can indeed pack a lot of stuff. And being able to do so also has other advantages, like hard drives are mechanical, they are less reliable, they consume more power. So being able to do this, all of this in silicon, kind of gives you plenty of advantages. Okay, so that's that memory. So in short, to recap the modules we saw, we saw decoder, we saw encoder, we saw multiplexer. We saw two types of multiplexer. Multiplexer where the control was one hot coded, and we saw the multiplexer where the control was binary coded, in which case it was basically the first type of multiplexer plus a decoder. We saw arbiter. We saw that how arbiter could be designed by ganging things together. We also saw priority encoder. We saw comparators, which again had this kind of bit slice design. And then finally we saw ROM. Common idea to a lot of these things is that we are dividing and conquering. There are some primitives like decoder, encoder, multiplexer, which combined different ways can be used to create different things. We saw, for example, how we could create a maximum function by combining a multiplexer and a comparator. So that's how we could create a max and other such functions. So, and we also saw that multiplexer and decoder could be used to create arbitrary logic, and ROM could also be used to create arbitrary logic. And then finally, this kind of bit slice assembly. You design a bit and replicate it. That's a powerful design paradigm that gets followed. So, one homework problem that I have given, this is not the design homework, but regular homework, goes like this. There is a simple card game where there are 4 players and each one of them just draws a card. And you have to find the winner, okay? As in who has the highest card. And the logic given to us is that ace is greater than king, queen, jack, all the way down to 2, kind of the normal one. And then the suit of the card is club is least, diamond, heart, and spade. And the problem describes how they are encoded. And you have to design a system where you are getting the 4 inputs, one from each player, and you have to output which is the winning card and who has it. Okay, and idea is that again you're kind of going to do it using these modules and all, and you can imagine comparator, multiplexers, those sort of things get used. So you can design a lot of interesting combination functionality using these kind of modules. Okay, so yeah, go ahead. How many what? Yeah. So what kind of example?
Can you do an example of that? When we're dividing into columns and rows.
When we are
Dividing into columns and rows.
Oh, okay, sure. So let's go back out here. Okay. So let's say so in this case already A was 8, and we divided into 6 and 2. So we have 6 bits here. We have 2 bits here. Okay, so our total number of memory locations is 2 to the power 8. So it is 256. Okay, we have organized it into 2 to the power 6 rows, right? Because I have a 6-bit coming in. So I have 2 to the power 6 rows, which is 64. And I have 4 columns. Okay, now let's say my address was 0, 0, 1, 1, 0, 1, 0, 0. Okay, let's say that was my address. And what I'm doing is I'm taking the top 4 bits, I'm feeding it here. So what I'm seeing is 0, 0, 1, 1, 0, 1 is out here. And the lower 2 bits, which is 0, 0, come out here. Now, this 0, 0, 1, 1, 0, 1 corresponds to 8 plus 4, 12, 13, right? So 13th row out here will be activated. So W13, so this means W13 would be 1. So one of these lines, let's say a row out here will get activated. All the rest W's would be 0. So the tri-state buffer in that 13th row, so let's say this was the 13th row, then these tri-state buffers, the tri-state buffer here and tri-state buffer here, they will all see an enable of 1. Whereas tri-state buffers in all the other rows are going to see that their enable is 0. So the ones which see an enable of 0 are cut off. These tri-state buffers, their input will now be appearing on the 4 columns. So on this column, I'm going to see 13th row, column 0. On this one, I'm going to see the data behind 13th row, column number 1. On the third one, I'm going to see 13th row, column number 2, and column number 3. But I'm interested only in column 0. So that's why the multiplexer comes into play. Whatever is appearing out here, I'm going to pass it through out here in this example. In this particular case, they are for D0, D1, D2, D3 are okay. Yeah, you're right. They're 16-bit each. So our memory is 16-bit wide. Yeah. So D0, this is 16 bits of data. D0 would be some number like, let's say, 0, 0, 1, 1, 0, 1, 0, 1, whatever, 1, 1, 1, 1, 0, 1, 0, 1, 16 bits. Okay, it would be something like that. Okay, and these wires that you are seeing running, they are 16-bit wide. So they are really 16 wires running.
So what do you mean by 256 and 16?
Well, I have 256 locations. Each one of them has a 16-bit number. Right? My address was 8 bits. Right? So I took 6 of them for rows, 2 of them for columns. So I have 64 rows. I have 4 columns. So their intersection, I have 256 locations. Each location is 16-bit wide. It will have 16 tri-state buffers feeding into a 16-bit bus. So my columns, these columns that are running, they are 16-bit wide. See how there's a 16-bit out here? So at each location, I have 16 parallel tri-state buffers. They're feeding into a 16-bit bus. Why are there 64 rows? Because, see, I fed 6 bits out here. So 2 to the power 6. Right? The decoder will have 2 to the power 6 lines. 64. That's what it is.
But why does that topology say
why? Okay, so just think in terms of originally my decoder needed to be 256 wires, right? 256 lines. In my original type of design, like this one, I would have taken all 8 bits of the address and created a decoder. So I will have 256 lines coming out and a single column, right? So that column will be running over a long distance, and I have a huge decoder. Now, what is happening is I have a smaller decoder, and total number of wires are 64 plus 4, 68. Okay, as opposed to 256 plus 1, 257. Okay, so fewer wires. And now even this may not be the best. Maybe you may want to split 4 and 4, as in have 16 rows and 16 columns. Now, where the right balance lies depends upon a lot of details, but what people normally try to do is to make the shape of the memory to be something which is squarish, okay, or something which kind of fits in the design. So there is no one correct answer to it. It depends upon additional constraints that you may have.
I'm not still confused with what because in this design more columns, right?
This design we have more columns, but I have 4 columns of 16-bit each. In my original design, I would have 1 column of 16-bit each. 1 column of 16-bit, right?
You have 4 columns more.
I have 3 columns more.
4 times.
I have 4 times 16.
And in the previous design, you have
1 times 16.
no, you have 4 times rows. Now we have 4 times columns.
I have 4 times columns.
So why is this one better?
Yeah, the reason is that in this particular case, it may not turn out to be better because I have 16 bits, but let's imagine my memory was only 2 bits. Then do you agree that this would be better?
Because we have 4 times more columns.
No, we don't have 4 times. We have 4 times a column, but I had originally 1 column. Now I have 4 columns, right? My rows went down by the same factor, right? So what's happening is that total number of wires are going down. If you go to my original example of 32-bit, right? 32-bit would have meant I would have 4 billion rows, right? If I have 16 plus 60, I will have 65,000 rows and 65,000 columns, right? In general, 2 to the power n plus 2 to the power m is less than 2 to the power n plus m. Do you agree with that? Right? 2 to the power n, if I have n plus m address bits, if I divide them into n and m, then in one case I have 2 to the power n rows and 2 to the power m columns. In the other case, I have 2 to the power n plus m rows. And generally speaking, 2 to the power n plus m is much, much larger than 2 to the power n plus m.
Another question, why do you say this one is slower?
Because I'm going through an additional, actually even the slow part is tricky, but I am going through an extra state of logic, right? Previously I was going through a decoder and a tri-state inverter. Now I'm going through a decoder, tri-state inverter, and a multiplexer.
But you are doing parallel.
I am
Parallel.
Well, it's not so much parallel, but this design may still be better because the wires are a lot shorter. So they have much less capacitance and therefore they will be faster. Okay, so those are unfortunately circuit details which some of you who end up doing EEM16 will get to see. Here, unfortunately, we won't go into it. Any other questions?
So they make physically, it might turn out to be even faster than.
Physically, actually, this design may turn out to be faster. So that extra multiplexer may not. It's that cost may be overwhelmed by the saving in the length of the wire. But again, I would emphasize, you guys don't need to care about these issues. Those are circuit issues which you'll learn later. Okay, so that ends this one. Let's look at another type of module. So we are going to look at numbers and arithmetic. So we already began to see a little bit of it. When we talked about comparator, we were thinking of our inputs as numbers. Only then the comparison makes sense. So we are going to build upon that to kind of look at more complicated things, adders, multipliers, and also could we have numbers which are signed? Could we have numbers which are real numbers or floating point numbers? So those are the kind of things we are going to look at. Okay, so recap thus far then again. So we have seen a generic way of designing digital logic. We've seen Boolean algebra, truth table, K-maps, sum of products, product of sums. We saw these building blocks and all. Now let's talk about numbers. So all of you thus far have seen binary numbers. We know very well how to represent positive numbers. So if I give you 0, 1, 2, 3, we know that if you tell me the largest number you need to represent, I need log to n bits with a ceiling, and then I can represent the number. So that one we know, and though it's kind of like our decimal system, but the only difference being that the value associated with a bit position goes as powers of 2. So position number 0 has a power of 1 or weight of 1. Position number 1 has a weight of 2, 4, 8, 16, and so on and so forth. So like our decimal system, but so 1, 1, 0, 0, 1 becomes 16 plus 8 plus 0 plus 0 plus 1, so it's 25. So we have seen this kind of stuff before. So question that we are interested in is, could we represent other kind of numbers, and could we then do arithmetic over them? Okay, that's kind of what we are interested in. So let's see how we can convert a decimal number to a binary number. Okay, so we know how to go from binary to decimal. Just add up the weights of the positions where bit was 1. Let's look at the other way around. So we want to go from decimal to binary. And that's important because in computers and all that, the human interfaces are always decimal, and then internally we seek to manipulate things in a binary fashion. So let's say we want to convert 17, which is in base 10, to a binary base. So what we do is we first try to figure out whether the number is even or odd. So we can do it by doing a divide by 2 and looking at the remainder. So we get 1. Then we want to find the next bit. So we look at 8 divided by 2, we get a remainder of 0. So it tells us which group of 4 do I lie in, and I kind of repeat this process. So divide by 2 again look at the remainder, divide by 2 again, look at the remainder, and now at this stage, remainder, and then finally 1 divided by 2, 0 with a remainder of 1, and then we are done. So that's what we end up with. So you basically start with your number, keep dividing by 2 until your quotient is 0, and then you basically line up on the remainders. This is kind of like how even in the decimal world you are given a quantity of things. You are first going to kind of see what are the leftovers. So I do a modulo 10, then I do a modulo 100, and then I do a modulo 1000. So I keep getting different digits based upon that. It's the same idea being applied out here. So we can try it out with some other number. So let's say 23. So 23 divided by 2 is 11, and I have a remainder of 1. Then I will say 11 divided by 2 is 5, remainder of 1. Then I have 5 divided by 2 is equal to 2, remainder of 1. Then I have 2 divided by 2 is equal to 1, remainder of 0. And then finally, I have 1 divided by 2 is equal to 0, remainder of 1. So my number becomes 10111, which, as you can check, is a positive. It's 23 if the number is treated as a positive binary number. So 10111 is what we do. So this gives us a general scheme. I can take any decimal number and play this game of repeated division by 2 to end up with my singular with the binary representation. Another common base of
on the previous slide, what is the LSB and the MSB stand for?
Oh, least significant bit and most significant bit. Highest bit, lowest bit. Analogy with decimal, least significant digit, most significant digit. Okay. So, yeah. Another base which is very commonly used is hexadecimal. Hexadecimal stands for base 16. The digits in base 16 will go from 0 to 15. If you are representing numbers in base n, then your digits go from 0 through n minus 1. And stylistically, the representation is after we hit 9, then we start using A, B, C, D, and so on and so forth. So that means for base 16, I need 0 through 9, and then I need A, B, C, D, E, F. I need 6 more digits, so they become A through F out there. So for example, F stands for 15, E stands for 14, D for 13, C for 12, B for 11, and A for 10. So let's say I'm given 1963 in base 10. So I can do what we previously did to come up with a binary representation, and in this case the binary representation is 111, 10, 10, 1011. To go to base 16, so if you think about it, 16 is 2 to the power 4. So each chunk of 16 corresponds to 4 bits. So what we do is we take our binary representation and we group it into groups of 4. So starting from the least significant bit size. So we have 1101, then so this group, 1011, we have second group 1010, and the final group only had 111, but we can prepend a 0 to it. It doesn't change the number, so we become 0111, and now I have 7AB, it's an hexadecimal. So it is written many ways. It's often written as 0x7AB. It's sometimes written as H7AB, sometimes written as 7AB base 16. There are all sort of representations, different people, courses, books, they kind of use different ones. Sometimes you may have ambiguity. So like if I just say number 79, in this course, you should always ask what is the base, right? I mean, we don't know whether base is 10 or 16 because this is also a valid base 16 number, but the value is very, very different. So base, from now on, sort of base is very important for you, okay, unless it is obvious from the context. So base 16 is very useful. Another base which is very commonly used is base 8. How many bits do you think will, what would be the grouping I would do to get base 8? 16 was 4, 3, 8 would be 3, right? What would be the digits in a base 8 number system? Base 10 has 0 through 9. Base 16 has 0 through 15 or F. Base 2 has 0 and 1. So let's give a clue, right? 8 should have 0 through 7. Always number of digits is 0 through n minus 1. So base 8 is very common. What other bases, I mean, any of you heard of any other civilization, society, whatever, using something other than base 10?
Babylon used base 16.
Yeah, Babylonians are base 60. That's where we get our 60 seconds and all that kind of stuff. Okay, so one of the oldest civilizations, they are a totally different base. Someone also told me that some of the South American civilizations also have used other kind of bases. So there have been other kind of bases for whatever reason have existed. Base 10, I guess because we have 10 fingers, have been the most common. Base 2 because we know how to represent 0 and 1. Base 16 because dealing with 0 and 1 becomes very painful. You are dealing with long strings of zeros and ones. So 16 lets you reduce by a factor of 4. So base 16's popularity comes from that. Computers do not natively represent base 16. I mean, they are binary. So it's just that groups of 4 we call as base 16. 8 bits are a byte. Anyone knows what are 4 bits called?
Nibble.
Nibble, yeah. 4 bits are a nibble. So hexadecimal digit is a nibble. Okay, but there are no. I guess there have been historically there have been some 4-bit computers long ago, 70s. But I mean, there's no such thing as nibble or 4-bit. It's not the unit normally we deal with, other than when we are reasoning about hexadecimal. Okay, so that's hexadecimal. Now let's talk about addition, binary addition. So specifically I give you 2 positive binary integers and I want you to add them. So we haven't learned about sign and all. They're just positive binary numbers. It's a string of bits, and so the key thing to keep in mind is when you see a string of bits, I also have to tell you how to interpret it. That string of bit may represent an ASCII character. It may represent a positive binary number. The same string of bit under different circumstances may represent a floating point number, a real number, a negative number, a signed integer, whatnot. So bits themselves don't really have any meaning. It's something that I ascribe to them. So what we are going to look at is I'm designing a combinational logic which is going to take inputs, and I'm telling you that those inputs represent a binary number. And we are going to add, we have to design the logic to add them. So if I have 2 1-bit numbers, the case is 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is what? 1 plus 1 is 1, 0, right? Because 1 plus 1 results in a carry. So it has to be the number 2, much like our decimal one. So looking at this, let's say I was, so you can say 0 plus 0 is 0, or another way of saying it's 0, 0. 0 plus 1 is 0, 1. 1 plus 0 is 0, 1 also, and 1 plus 1 is 1, 0. So anytime you add two 1-bit numbers, in general, you will get a 2-bit number. Okay? Just like when I add two 1-digit numbers, I may get a 2-digit number, right? 9 plus 9 is 18, so I need an extra digit. Carry. So that's the 1-bit case. Now let's say multi-bit. So in multi-bit, I'm now giving you two n-bit numbers. You have to add them. Much like we do a regular arithmetic thing, we start with unit place and keep doing carry. So that's the same thing we want to do out here also. So let's say these are our numbers. I have two inputs, 6 and 3. 6 is 110 and 3 is 011. So let's take by analogy with our arithmetic, normal decimal arithmetic. I'm first going to add the least significant position. So I have 0 and 1. 0 plus 1 is 1 with a carryover of 0. So there's no carry. Next position, 1 plus 1 is 0, but so it gives me a 0 with, let's see, yeah. So 1 plus 1 gives me a 0 with a carry of 1. And then finally, now what I have is I have a carry of 1 coming in, and I have a 1 here and I have a 0 here. 1 plus 1 plus 0 is 2, so I put a 0 here and there's a carry out of 1. So my total output in this case becomes, this carry comes out here, 1001, which makes sense because 1001 is 8 plus 1, 9, which is what we expect. So you have to replicate the decimal addition process, but now you are working with bits. Your carries could have the value 0 or 1, whereas and you're going to when you are adding the next bit position, you have to add them together. Okay, so let's try this one. 5 plus 7, we want it to be 12, so help me out. What would be 1 plus 1? 0, and is there any carry? Yeah, right? Carry out here. Now we have 1 plus 0 plus 1. 0, and a carry of 1 again. And now I have 1 plus 1 plus 1, that's 3. So I'll get a 1 and a carry of 1. And that carry comes out here. This is what I end up with, which is 12. Right? So what's happening is at every bit stage, if you think about it, I'm computing two things. I'm computing the value at that bit position, and I'm computing the carry. And in every bit position, my input, I have three inputs. The A and the B bits, as well as the previous carries, right? Just like in regular addition, the 2 digits and the carry. So I have three inputs, carry in, A and B, and I have two outputs, sum and carry out. So the combinational logic for each bit position is going to have 3 1-bit inputs and 2 1-bit output. And I'm going to chain them together. So yeah, we just did it ourselves, so don't worry about it. Okay, so let's see. So what is happening at the ith bit position? So least significant bit, all we are doing is we are adding 2 bits, one from each input, and I have the output which could be either 0 or 1 or 2, and depending upon that, so I need 2 bits, one of them is a carry bit and the other is the output in that bit position. So we call them as sum and carry. In other bit positions, I am going to see something different. So let's first see what is the logic for bit position 0. So I have 2 inputs, AI and BI, and I have 2 outputs, the sum for the ith and the carry which I'm going to give to the next bit location. So if my inputs were 0 and 0, my output value should be 0, which means carry is 0 and sum is 0. If input was 0 and 1, that means my output is 1, which means the sum is 1 and carry out is 0. I have the same thing for 1, 0, and then finally Okay. Finally, we have 1, 1, whose value is 2, which means I have a sum of 0 and a carry of 1. So this truth table is called a half adder. A half adder takes two 1-bit numbers and produces a sum and produces a carry. It is used usually in the least significant bit because there is no carry coming in there. So let's look at this. What do you think is the logic equation for S of I? Does it remind you of any particular gate we have seen? Huh? XOR, exactly. So this is nothing but an XOR. What about this guy? The carry out. What is that? AND, right? So our half adder is nothing but an AND gate and an XOR gate, right? XOR is computing the sum and AND is computing the carry. So that is what we have. That's a half adder. And that's the truth table, which we already saw. So half adder can handle the least significant bit, but it still cannot handle a carry incoming in, right? It's only taking input AI and BI. So now we need something more complicated. So, okay. So what happens in other bit positions? In other bit positions, I have three inputs. I have the two input, one bit from input A, one bit from input B, but I also have the carry in, and I have to factor that in. Now, if I'm adding two 3-bit numbers, our worst case is 1 plus 1 plus 1, which is 1, 1, which I still means I only need 2 bits. One of them will be the sum bit, and the other will be the carry bit. So my truth table looks like this now. It has AI and BI, but it also has CI, which is the carry in from the previous bit coming in. And I'm going to output sum, and I'm going to output the carry for the next stage. So now I have 8 possibilities in the truth table, and I have 2 outputs. So for example, if all 3 are 0, output is 0 and 0. If it's 0, 0, 1, then I want an output value of 1, which basically means sum is 1 and carry is 0. You repeat the same logic like this. So let's take another one like 1, 0, 1. 1, 0, 1 means I need an output of 2, which means my sum is 0 and carry is 1. Or if all 3 were 1, then my output value is 3, which means I need 1 and 1. This truth table is called a full adder. A full adder takes 3 inputs, 3 1-bit inputs, and produces a sum and a carry. So 3 1-bit inputs, and it's producing a 2-bit sum. Basically, 2 bits of output. One we put in the current bit position, the other we hand over to the next bit. Okay, so looking at this, how can we implement it? So now let's look at this one. So let's look at carry first. Carry is 1 in this row and in these 3 rows, right? It's 1 when either 2 of the inputs are 1 or all 3 of them are 1, right? So it's 1 when A and B are 1, when C and B are 1, C and A are 1, or all 3 of them are 1. And this should remind you of the majority circuit. It's basically saying majority of the bits are 1, right? I have 3 bits, and if 2 or 3 of them are 1, then carry is 1. So carry is being produced by a majority circuit. What about sum? So if you look at sum, so remember, we had previously defined XOR gate as a gate which outputs are 1 if an odd number of its inputs are 1. That's how I had defined a multi-input XOR gate. So a 3-input XOR gate is going to output a 1 if either one of the inputs is 1 or 3 of the inputs are, all three of them are 1. Okay? And if you look at this, that's exactly what's happening out here. It's 1 here, it's 1 here, it's 1 here, and it's 1 here. In this first case, only BI is 1. So we have a single one. In the second case, AI is 1. In the third case, CI is 1. And in the fourth case, all of them are 1. Okay, so sum is high when either one of the three inputs is high or all three of them are high. And that is a 3-input XOR gate. So my full adder looks like this. It's a majority circuit to produce the Cout, and it is the 3-input XOR gate to produce sum. How can you implement a 3-input XOR gate with 2-input XOR gates? Anyone? What do you think this circuit would do? Let's try it. So what would happen out here? So in this case, let's say A, B, C is, if A and B are equal, output would be 0. If one of them is 1, the output would be 1. So if this guy is 1, that means one of A or B is 1. Now if C is 1, then that means I have an even number of 1s, because I have, if C is also 1, then that means I would have an even number of 1 and I would want an output of 0, which is what this XOR gate will do. If on the other hand C is 0, then I have an odd number of 1s, I'm okay out here. So if you kind of intuitively think about it, you would see that two input XOR gates are equal to this stuff is equal to this 3-input XOR gate. So a 3-input XOR gate is two 2-input XOR gates in series. And in fact, you can construct more XOR gates like this. One of the homework problems that I handed out kind of touches upon this topic. So just remember, an XOR gate basically lets me essentially check for an odd number of 1s. Okay? And if I gang them up, it is basically creating a multi-input XOR gate whose property again is it checks for an odd number of 1s. Majority circuit, how will you implement that? So let's say I have A, B, and C. What's the majority? Tell me an equation for majority. So majority is again, majority of the inputs are high. A, B, or oh gosh, I don't know why it's saving again and again. A, B, or AC, or BC. Does everyone see that why it works? You plug in, if all three of them are high, output will be high. If any two of them are high, the output will be high. So this is our majority circuit. So I can implement majority circuit using this equation. I can implement the 3-input XOR gate using 2-input XOR gates. So full adder, therefore, so full adder truth table, which we already saw, and the circuit which is designed. So full adder for other bit positions other than 0, takes the carry in, produces a carry out, and produces a sum. And your regular adder then basically becomes, okay, we'll touch upon it next time briefly, but your regular adder now becomes a half adder, followed by a bunch of full average in series, and that's where you get your index.